All right, so here we go. This is problem number 9. It's the car on a circular track problem. So here's what it tells us. It tells us that the car has a mass of 1,200 kilograms. It's on a circular track with a radius of 150 meters, and the coefficient between the coefficient of friction between the tires and the track is 0.60. As we talked about a little earlier today, that's got to be static friction because we're trying to prevent the car from sliding. Okay, emphasis on the word sliding. So A says, what is the fastest the car can go without skidding, without sliding? All right, one of the things I want to encourage you guys to do when you get to these problems that are a little bit more involved is make a free body diagram of the object that's traveling in a circle. Okay? So for us, we've got a car that's driving in a circle, right? So here's the car. I'm going to draw a front view of the car. Here's Roy. Hello. Here's the wheels. Okay, cool. Good? All right. Here's the curve. So it's like doing this, coming out of the board. Follow? All right. So name the forces on it. What do we got? Shout them out. What's the first force we should always draw? Gravity. Force of gravity is 1,200 times 9.8. That's negative 11,760 newtons. What force can I put now? Normal force, right? I know the car is not going to fall because it's on the road, right? So the road must be pushing it up. So here's my normal force. It's got to be positive 11,760 newtons. And there's one other force. Static friction, right? Okay. So one of the mistakes I see people make sometimes is they'll just go, oh, and there's centripetal force. So first of all, is everybody cool with why I put the centripetal force pointing that way? All right. So centripetal force isn't this magic force that just comes from nowhere. Something has to exert that centripetal force to make the car go in a circle, right? Does that make sense? All right. And in this problem, like Michael just said, the centripetal force is provided by the static friction between the tires and the road, right? So this is equal to force of static friction, right? Follow? And if we're trying to maximize the velocity, we want to maximize this force, right? Good? So I now have, this is exactly what I was talking about before class yesterday. Not before class, at the beginning of class yesterday. We now have two equations to find our force of our centripetal force. We can do mv squared over r, and we can do coefficient of static friction times normal force, right? So let me pause there for a minute. Does this make sense? Okay, so the question wants us to find the velocity. We're trying to find that maximum velocity. So thoughts about how to find it? Sure.
You have enough information to calculate the FC, which is the force of static friction top to bottom.
Oh, yeah.
And set that equal to the other one, and you have enough to only have the one variable.
So I think what I'm hearing you say is that I know my coefficient of static friction and my normal force, so I can use this to find my centripetal force. It's going to be 0.60 times 11,760. Yes? What's that give you? Oh, I guess I could pick up my sheet right here where I had it actually worked out. Motion basics, what is this number? 7, 8, 9. I might as well dig it up because we're going to need other numbers here in a minute. So that gives you 7,056, which is exactly what Michael just said. I apologize. Oh, a quick note about this, you guys.
Isn't that static friction?
Yeah.
No, it says FC.
Yes, but remember, our FC is equal to our static friction.
Yeah. Okay.
Right? Like they're literally the same force. Good? Like you guys remember that elevator problem, and some of you guys had force of elevator and normal force labeled separately? And I kept saying to you, no, 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 those are the same force. The elevator provides the normal force, right? Same idea here. Static friction provides the centripetal force. So they're literally the same force. Literally in the literal meaning of literal, not literal in the... Good? Okay. All right, so there's my centripetal force. Everybody good? So Josh's point was, oh, right on, cool, now I know my centripetal force, I can plug it in up here and find my velocity, right? Because I know my mass, my radius, and my centripetal force, so plug them in and you can find the velocity. Follow? All right, so if you do that, that velocity turns out, is it okay if I just write down the answer? Does everybody follow what I'm saying here? To me, this was the important part. I wanted to talk about that drawing. Okay, so this, if you find the velocity, you get 29.7 meters a second squared. No, meters a second, sorry. Everybody cool? All right. And then the next question says, what's the centripetal acceleration? So that was part A. Everybody good? Like your hat. All right, part B wants to know the centripetal acceleration. So centripetal acceleration is just v squared over r, right? Follow? Yep. So plug in our numbers. We know the velocity, we know the radius. Plug in the numbers, and you get 5.88 meters per second squared. All right, so let me pause that all for a second. Is everybody okay with that? Okay, now, a couple quick comments. Go, brain, process. Oh shoot, I'm worried I made a mistake on this. Oh, no, I'm good. Oh, it doesn't ask that question. Oh yeah, it does. Oh, that was all. What am I doing? Somebody tell me what I'm doing. Okay, yeah, we're good. Sorry. Okay. Sorry, my brain just, I was thinking ahead. All right, so is everybody good up here? All right, a quick comment about this. When you use the centripetal acceleration equation, the sign is meaningless. Okay? Please don't think, oh, this is positive. The centripetal force has to be in a positive direction. Because think about it. If you're going in a circle, the direction of your centripetal acceleration is always changing, right? Do you know what I mean? So this is just the magnitude of the centripetal acceleration. The direction is always inward. Follow? All right, any questions up to there? All right, so in my brain, everything here is test-worthy. Follow? From this point forward, things are a little bit more advanced probably than I would put on a test. Okay? So I'm going to kind of run through the rest of this a little bit more quickly. So everybody's good up to here. Okay, so moving forward then. Part C has 3 Roman numerals, which is why I got tangled up a minute ago. I got my letters and my Roman numerals mixed up. C says if the car slows down and stops from the speed in part A, then A, what's the tangential acceleration at this time? All right, so here's the deal. In the video, I really briefly talked about, I think it was actually in video 5.1 that I talked about tangential velocity. Yes? Briefly? Okay, so here's the deal, you guys. Remember, you guys, velocity is speed and direction, right? So in this problem, I've got a car going in a circle. Good? So sometimes it's going this way, sometimes it's going this way, sometimes it's going this way. So technically speaking, the velocity is always changing, right? So when I say to you, find the velocity, technically all we're doing is we're finding the magnitude of the velocity, right? Okay? To describe the direction, we just say that the velocity is, so from geometry, do you guys remember, what does it mean for a line to be tangent to a circle? Sure, we got.
So it's basically a circle where only one point gets touched by another one.
Good. Yeah, a line that's tangent to the circle touches the line at exactly one point. So it turns out if you're traveling in a circle, your velocity vector is in the same direction as the tangent line. Okay, so that's why it's called tangential velocity. Cool? Yes?
What do you mean by magnitude of the velocity? Like
Magnitude is the number part. So like your velocity has 2 parts, right? Like, oh, I'm driving at 60 miles an hour north.
Never mind that.
The magnitude is the 60 miles an hour. Good. I should use that word more often because it's an important word for you to know when we talk about vectors. All right, everybody good? Okay. So in this problem, here we go. So part C. We want the car to stop in 6 seconds, right? So here's the idea. My tangential velocity initially is 29.7 meters a second, and we want the car to stop. So our tangential velocity final is going to be 0, right? And we want this to occur in a time of 6 seconds. That's a 6. Follow? So our tangential velocity is accelerating. So our tangential acceleration is final minus initial over time, right? So solve this and you get negative 2.48 meters a second squared, just because how fast you're going is changing. What's wrong, Josh?
Is it not 12 seconds?
It's totally 12 seconds. Sorry. Right answer, wrong time. Sorry, the 6 seconds comes up later. All right. Does that make sense, you guys? So what that represents is the fact that the car is going in a circle but slowing down. So these velocity vectors are actually getting shorter, right? So what direction would that tangential acceleration point? And you can't point to answer this, unfortunately. So in my drawing, the car is going, what? Counterclockwise, right? So what direction is the tangential acceleration pointing? Clockwise, right? Against the velocity, right? So these are my velocity vectors. My acceleration vectors are going to point the opposite direction, right? Follow? All right, shoot, I want to get through 9. I want to get through 8, so we need to finish this up. Okay, oops. All right, so that's that. That was what, Roman numeral I? Roman numeral 2, what's the velocity after 6 seconds? So you're just going to do Vf equals Vi plus At. So our initial velocity was 29.7. Our acceleration's negative 2.48. Here's where the time is 6 seconds. And you end up getting 1.47 meters a second squared, or meters a second. Follow? So somewhere between here and here, there's a point where we're traveling at that velocity. Good? All right, and then Roman numeral 3 says what's the centripetal acceleration at that point? So AC is V squared over R, so I'm just going to take that velocity.
That's the acceleration.
Okay.
You skipped 2 and 3. Like you flipped on.
You have the answer for 3 on number 2.
Oh, I see. Gotcha. Thank you. Sorry, I'm trying to hurry so that we can get through number 9, which I want to, or number 8, which I want to talk about. All right, are we good? Thank you. Everybody set or no?
Yeah.
Okay, so now do you guys agree we can plug in the acceleration to get the plug in the velocity to get the acceleration?
Yep.
All right, so if you do that, that gives you 1.47 meters a second squared. All right, everybody good?
Yep.
All right, so last step, Roman numeral 4 wants the overall acceleration. So this is the deal with this, you guys. This is the first time we've done something like this. We've got acceleration now occurring for 2 reasons. The car is slowing down, so there's a change in speed, and the car is turning, so there's a change in direction. So how do we find the overall acceleration? Well, here's the deal. So where do I want to draw this? I'll draw it right here. So somewhere in here, so we decided that so I'm going to draw the acceleration in blue. Okay? So we decided that the car had a tangential acceleration of negative, what was it, 2.48? Is that right? Good? All right. And at this point, the car is traveling at 14.8 meters a second. So there's also centripetal acceleration, right? So at this point, you guys, everybody point for me. What direction does the centripetal acceleration point in? In toward the center, right? A couple of you are pointing out. Remember, the centripetal acceleration is always directed toward the center of the circle, right? Okay? So here's my centripetal acceleration. what was it? Is that 1.48 also? 47. Cool? What's that?
It's a vector.
Good. Yeah. Look, I've got two vectors here, right? I've got one component and another component. And what's true about those two vectors?
Perpendicular.
They're perpendicular, right? Because one's tangent to the circle and one's along the radius. Cool? So how do you find the overall acceleration?
A squared plus B squared.
Just do a squared plus b squared equals c squared. Right? So I'm going to go, all right, well, when you add vectors, how do you have to position them? Head to tail. Good. So I'm going to go, here's my centripetal acceleration. Here's my tangential acceleration. Here's my overall acceleration. Here's my right angle. Okay? So my acceleration's actually this way. Some of it is towards the center to turn it, and some of it is against the motion to slow it down. That's tough. I wouldn't do it like that on a test. All right. Good? Yes.
So when the object that's moving in a circular motion isn't speeding up or slowing down, is there no tangential acceleration?
That's exactly right. Yeah, and that's all I'll give you on tests. Yeah, so if you didn't just hear it, Nate just asked a really good question. He just said, so if the object isn't speeding up or slowing down, is there only tangential acceleration? And the answer to that question is a resounding, very important yes. Did I say that all right? If the object isn't speeding up or slowing down, your only acceleration is centripetal.
Yeah.
I said tangential, didn't I?
Yeah.
The only acceleration is centripetal. Cool? Ugh, I apparently haven't had enough coffee yet. I got Einstein's today, which isn't as strong as my usual brew. All right. Are we good? All right. Cool. So that's a neat problem. Definitely harder than anything I'd give you on a test. But I like it because I think it really illustrates this idea about the centripetal force being directed towards the center. Cool? All right. So that was a lot of me talking. Unfortunately, we have to go through the number 8, the rotor problem. All right. I'm just going to hit the last part of it. Am I safe in assuming everybody got the first chunk of it pretty safely? Like at least up through the centripetal force, the 2,211 newtons? Did everybody get up to there okay? Is that the right number?
Yeah.
Okay. All right, so I want to do the last half of that problem. So before we do, I want everybody to go and take a second to clear their heads. And then look at this problem and think about the positioning of the three vectors that are on it. There are three forces on this. Gravity. Why doesn't the car fall? Because there's a normal force. What allows the car to turn? Centripetal force, yes? And the centripetal force is provided by static friction. Cool? All right, so let's jump back then to number 8, which is the rotor problem. Okay, so in that problem, here's what we had figured out. Obviously, we're not going to get to our target check today, which is fine. We will be doing it Monday, though, just as a heads up. So here is what we have figured out at this point in our story. So we've got, so here's the ride. Here's Sally. Is it Sally that's on the ride, I assume? Look how much fun she's having. She has no neck. That's if she was Ed Sullivan. Nobody knows who Ed Sullivan is. Okay, let's see. So what we had figured out at this point was that the centripetal force in part E, we figured out that the centripetal force on her was 2,211 newtons. Is everybody okay up through part E? All right, so F says, what provides this force? Is it friction again? No. What's keeping her going in a circle, you guys? Why doesn't she go flying outward? The ride pushes her inward. Specifically, the walls of the ride push her inward, right? Okay, what's that called when an inanimate surface pushes a thing? Normal force. So in this problem, this is weird. Our centripetal force is an inward force by the walls, and because it's a force from the walls, that's the normal force. Does Does that make sense? 7 years ago, we did a problem in which we had a book or a picture or something being held against a wall like this, right? Okay, and you guys remember that? Our person was pushing this way, and the normal force was this way, right? So this is basically the same thing. Okay? Now, what other forces act on Sally in this problem, you guys? Force of gravity. Gravity's pulling her down. Her mass was 56. So 56 times 9.8 gives us 548.8 newtons. Good? Now, here's the tricky part of this, you guys. Gravity's pulling her down, but she doesn't fall, right? Like, that's the cool part of this ride. Okay? So do this for me. Does everybody know what I'm talking about, the rotor ride from the video? All right, suppose had you guys seen that ride before?
Yeah.
Yes? Okay. They don't make, I haven't seen one. Have you guys seen one anywhere recently?
Not recently, but
St. Joan of Arc? Is it like that? Or isn't that the one where you slide up the walls?
No, you're on like a thing where you do slide up,
Okay.
but you're still going up.
I gotcha. Okay, so anyway, so suppose you were describing this rotor ride to somebody who had never seen it. So somebody do that for me. How would you describe it to somebody who had never seen that ride? The ride spins around and then what happens? Well, it pushes you against the wall really hard, and what do? You get pinned against the wall. Do you float?
Well, like,
Oh yeah.
that's not what
Should I refill my coffee cup? What do, you guys? Explain the ride. What do? Come on.
It spins really fast and you stick to the wall.
That's the word I wanted! It spins really fast and you stick to the wall, right? Why am I excited about the word stick? Ooh, friction! You stick to the wall. You don't slide down the wall. It's static friction. It's static friction that prevents you from sliding down the wall. Right? It's static friction. That's why you don't slide down the wall. How much static friction?
about 500.
548 newtons. Does that make sense, you guys? Right? It's got to be, because otherwise you would slide down the wall, wouldn't you? That is the exact same thing as this, except because the ride is spinning, the reason there's a normal force is not to resist me pushing. There's a normal force to produce the centripetal acceleration. Okay? This is the same thing though, right? Gravity's pulling this down. It doesn't fall because of friction. Follow?
follow.
All right, cool. So, from this point, we're done. Our centripetal force is 2,211 newtons. So glad I recorded all that. Remember that time Mr. Hacker got fired? Okay. All right. So so now we can find our coefficient of friction, right? So let's see. Our force of friction, we just decided that was 548.8 newtons. Our coefficient of static friction is the thing we don't know, and our normal force is 2211. And now you can solve and find your coefficient. Follow? All right. Moral of the story is when you're solving these problems, you have to figure out where that centripetal force comes from. Sometimes it's friction. Sometimes it's normal force. Sometimes it's tension. All right? How about the moon orbiting the Earth? Sometimes the centripetal force is equal to gravity. Cool? Questions on it? All right. Let's see. How about a merry-go-round spinning really fast or holding onto the handlebars? What provides the centripetal force?
You're pulling yourself.
You can't pull yourself, so what are you doing?
You're pulling the
You pull the handlebars
Handlebars outward.
outward. What's the reaction? They pull you inward. There's your centripetal force, right? Cool? questions on that, you guys? All right.